All right, so we're going to cover a little bit more of motion. We'll talk about projectile motion. That's motion of objects that are being thrown or launched into the air. But before we get into that, I just wanted to give you guys a quick reminder. Next week is going to be our first exam. Our first exam will cover, as we've been talking about, motion in different aspects. We'll talk about, you'll be given problems with one-dimensional motion, straight line motion. You'll be given problems with two-dimensional motion, that's rotating, or projectiles. You'll be given motion that is constant acceleration, speeding up, slowing down, or perhaps even turning. In order to prep for this exam, your fourth homework assignment is pretty short. It's only 4 problems of projectile motion. That being said, the 4 problems are not going to be the quickest in the world to solve, but it should be a little bit faster than your previous homework assignments. Why did I do that? I did that because your focus for this week should really be study. And to encourage you to think about how you're going to study, your discussion board post this week is going to be you guys describing to me what your plan is for studying. You're going to put down, I'm going to spend this many hours studying old problem sets, or whatever you're going to do. On Canvas, if you look at that discussion post, there's a link to a sort of a review document, a study guide type thing with a bunch of practice problems at the end of it. And the answers to those practice problems. I made one by popular request. I encourage you guys to look it over. For your exam, you will be allowed your calculator, whatever calculator you got. As for notes, you're not going to be allowed your own cheat sheet. Instead, you're going to be allowed your little note cards that I've been handing out to you. I'm going to hand out this last one today. This last one has some stuff on significant figures and unit conversions. The type did come out pretty small on it. I did not anticipate it being as small as it is. So if you have trouble seeing it, I can print you out one with bigger fonts, but those are the ones that we have for right now. So you'll be allowed those equation note cards, pen and pencil, and calculator. If you want to listen to music while you take the test, you are welcome to, but just be aware that whatever playlist you pick, you gotta like it because it's the only one you're gonna listen to during that test. Cannot change it halfway through. Are there any questions as it pertains to the exam? Any thoughts, any comments? All right. So now we've been discussing motion, right? We've been discussing motion over and over and over. We use certain quantities to describe motion, right? We start every lecture talking about these different quantities. What quantities do we use to describe motion of different objects? Quantities might we use? Position and displacement. Position describes what? What does position describe? Who wants to give an answer? What does position describe?
Where the object or whatever it is.
Where the object is, where the location of the object is, or where it's going to be, or where it started, or where it ends. That's exactly right. The position, where an object is located. Displacement, well, displacement describes what? Turn to your neighbor. Tell your neighbor what displacement describes. If you're not talking to your neighbor, I'm liable to pick you to tell me what displacement is. All right, the gentleman with the white shirt right here, what is displacement?
Distance travel.
Distance traveled, kind of. It's your change in position. Sometimes that is the distance traveled. Sometimes those are 2 different quantities. But we would say specifically, it is your change in position, your delta x, your delta y, your delta theta, if we're talking rotational motion, right? Your change in position, where you ended up subtracted from, or where you started subtracted from where you end up. X final minus x initial. So that's position, displacement. What other quantities do we use to describe motion? Velocity. Velocity is a description of what, though? What does velocity tell us? Turn to your neighbor and tell your neighbor what velocity means. If you're not talking to your neighbor, I'm liable to pick you to tell me what velocity is.
So it's shorter. Yeah, do alternatives instead of like small.
All right, so what is velocity? Who wants to share their definition of velocity? Who wants to share? I can call on someone. Right? Speed, okay. Speed is a good description. Speed is only half of the quantity of velocity, right? Speed tells you how fast you're going, but velocity being a vector means it needs what else, along with how fast it's going? Direction. So it's speed with direction. You know, it's 60 miles per hour north. The direction is important when it comes to velocity. It's very important when it comes to velocity for today. Now, the other way we can describe velocity is by the rate of change of your position. How quickly is your position changing? That's what speed essentially is. Speed tells you how quickly you're moving, how quickly you're going from one location to another. So velocity tells you how quickly you undergo your change in position or how quickly that displacement occurs. If we're using calculus, we would say it's the derivative of the position. And that tells us our velocity. Now, velocity can change. And if we have a changing velocity, what quantity might we use to describe that changing velocity? Acceleration. Acceleration tells you how your velocity is changing. Acceleration tells you about how your velocity is changing, and specifically how quickly that velocity changes, dv dt. Acceleration is dv dt. Now, velocity is a vector, right? We say velocity is a vector. Why? Because it depends on which direction you're going. Again, 60 miles per hour north is different than 60 miles per hour south. You'll end up in vastly different locations or vastly different positions. So when it comes to velocity, direction absolutely matters. It's a vector. Acceleration, well, acceleration also is a vector. Acceleration has directionality, and that direction is very important. Because when we talk about an object that is moving, well, if it's under the influence of gravity, that object will accelerate downwards. Not left, not right, not up. That acceleration will be downwards. And that downwards is important because it tells you the difference between an object falling or an object somehow floating up into space. So direction is important when it comes to acceleration. We've described our directions by saying, it's left, right, up, down. We have our left and right motion or horizontal motion, which we typically represent with the letter X. We say X is our horizontal motion. And we can say, if we have an object that is moving horizontally, perhaps we say an object rolls along a flat surface at a velocity equal to 2 meters per second. And in fact, I'll give you 2.0 for sig figs. 2 meters per second in the i-hat direction. That is our velocity. Now, if an object is rolling along a table, neglecting any sort of frictional forces that might be involved, if an object is rolling across a surface, we can safely assume that the acceleration on this object is 0. So our acceleration on our object rolling along a flat surface can be assumed to be 0. Don't put the i-hat on there. Why not? Just to tell you, 0 in the horizontal direction. In other words, we can write this as saying our velocity in the x direction is 2 meters per second, and our acceleration in the x direction is 0. By putting that subscript x in place there, it tells you that this is the piece that multiplies that i-hat component. If it was moving to the left instead of the right, we might say it's -2. And it would be -2 I hat for your whole velocity vector. Does this make sense? Does this seem all right? Yes?
So, where it says a flat surface,
Yeah.
that lets us know that acceleration is 0?
Yeah, because it's not going to be tilting downwards, meaning it's going to roll down the table. It's just moving along the flat
And you
surface.
said no resistance,
No resistance.
no friction.
No friction. Now, in the real world, of course, there'll be friction. But we can safely assume in this initial model of an object rolling, friction is pretty negligible. Friction is nearly 0. And if friction is 0, then that gives us a 0 acceleration. Yes?
So that means the velocity will be constant, right?
Absolutely. Absolutely. The velocity is constant. How did you know that?
Because if acceleration is 0, every velocity will stay the same.
Exactly. If your acceleration is 0, well, that means your velocity is unchanging. Acceleration is how quickly your velocity changes. So if acceleration is 0, that means you have no change in velocity. That means velocity is constant. What does that mean when it comes to our mathematical models? That means your initial velocity is in fact your final velocity. That is absolutely true. Now, under this case of constant velocity, meaning 0 acceleration, under this case of constant velocity, we know that the change in position, but we can also call the change in position what? Displacement. Your change in position or your displacement is simply given by taking that velocity, multiplying by time. And here I'll specify x because we're looking at horizontal motion. But velocity times time will give you your displacement. Now, had it been accelerated, had we had some acceleration, there would be an additional piece here. If our object was accelerating, we would have an extra plus 1/2. Oh, jeez. 1/2 acceleration times time squared. That's the full kinematic equation. Full kinematic equation. But this term ends up being 0. Why? Because your acceleration is 0. This equation still holds, and this is the equation that is on your little note card. If you go to your green note card, flip to the constant acceleration equations, this full one is on there with the 1/2 at squared. But here that 1/2 at squared is taking 1/2, multiplying it by 0 gives you nothing. So we have that the change in position of our object rolling across the surface is going to be given by your velocity multiplied by time. So then we ask the question, perhaps. Then we ask the question, how far does did I say an object? Yeah, how far does the object, whatever this mysterious object is, how far does the object move after 3 seconds? How far does the object move after 3 seconds? Well, this isn't so bad. We've done this. We've taken we take our velocity, we multiply it by time. 3 times 2 gives you what? 6 meters. So our change in position, our displacement here, is given by 6 meters. That's not so bad. And then we take a look at this and we say, well, that's easy. We had 0 acceleration. What happens when we start to have acceleration? What happens if we were to look at an object, perhaps, that is moving vertically under the influence of gravity? Well, if it's moving vertically under the influence of gravity, we say that this is free fall motion. And again, we'll ignore air resistance. We'll ignore any sort of frictional forces that come about because of an object moving. So we'll have our vertical motion be represented by free fall motion. All right, well, if this is the case, we traditionally use y to represent our vertical motion. And with our unit vector notation, these I hats and these j hats, and if you have that third dimension k hat, we would represent it with a j, right? So we say an object perhaps, an object is released from 20 meters, I'll put a decimal point there to indicate 2 sig figs. An object is released from 20 meters above the ground. How long until it hits the ground? Yes.
For the horizontal, even though it's on a flat surface, it's still gonna slow down by its own. But I mean,
It would only slow down if there was friction. Friction would serve to slow it down. So by saying that friction is negligible here, the acceleration would be zero. Things don't inherently slow down. They slow down because of external forces. So assuming friction is negligible, we would say acceleration is zero. If there was friction, it would slow down. But we're going to assume best case scenario friction is negligible. And for rolling objects, that tends to be a good enough approximation. All right. What other questions we got? Feeling all right? Yes.
Is this supposed to be plus in the thing? Because it's minus on this.
That's where if you use V final.
Oh, okay.
So on your note sheet for the constant acceleration, there's a version of this equation that uses V final, and there's a minus sign for the acceleration term. There's a version that uses V initial, and there's a plus sign. Be sure to remember finals and initials are different. Now in this case, for our horizontal motion, our final velocity is the same as our initial velocity. So kind of doesn't matter which one you use there. You can use final velocity, you can use initial velocity, and that subtracted off term will go to zero anyway. All right, any other questions? All right, so we have this free fall problem. Now, in the free fall problem, we're only given one number. We're only given directly the 20 meters. What is that 20 meters? Well, the 20 meters is how far we have moved. 20 meters is what quantity?
Displacement.
Our displacement. And specifically, we might say that our displacement delta y is equal to 20 meters in the negative j hat direction. That negative tells us what? That it's going down, absolutely. So this is the only value that is directly given to us, but there's more that we can assume. There's more that we can tell from this problem, such as we actually know what the initial velocity is. What is the initial velocity? Zero. The initial velocity is zero because it's released. It's released. It's not thrown, it's just let go. You let go of something, it's not going to magically start with some speed. It has to build that speed up as it falls. So your initial velocity is zero. Well, we also know one other piece of information. We know what the acceleration is. What is the acceleration? 9.8 meters per second squared, but I heard something else with that 9.8. Negative. Negative. The acceleration is negative 9.8 meters per second squared in the j hat direction. That negative is important. It tells you that's the direction of the acceleration. Whenever an object is in free fall, the acceleration is always negative 9.8. So we can take this and we can say, well, this is equal to, if we wanted to use that constant g, negative g j hat, where g represents positive 9.8. Yes, the variable g, the letter g, we say is positive 9.8. And we incorporate the negative outside of that value. In any case, we have our problem, we have our known values, and we can take our known values and plug them into our equation that says perhaps delta y is equal to the initial in the y direction times time plus 1/2 the acceleration times time squared. We say this will tell us, without a doubt, the relationship between position and time for our object. And we take this and we say, all right, well, the initial y is equal to 0. And then we have 1/2 our acceleration, which is negative g times t squared. And there's a j hat in there, so negative g j hat. We look at this and we say, well, delta y is equal to what? Negative 20 meters per negative 20 meters j hat. So that's our delta y is equal to negative 1/2 gt squared j hat. I'm moving that j hat component, or that j hat piece, just algebraically. Doesn't matter the order in which you multiply in. You can always multiply in whatever order. When you do this, you see something. You see that the j hats cancel out. You also see that the negatives will cancel out. And you get 20 is equal to 1/2 gt squared. You can solve this for the time. You can see how long does it take for it to move. 20 meters is equal to 1/2 9.8 times t squared. And it's just a little bit of algebra to solve this. Go ahead, solve this. Check with your neighbor, make sure you get the same time. I'm pointing them out right here. So there's a question that was asked about, do you always want to include the j hats and the I hats when you're setting up problems? The most surefire way to make sure you have all the right components in all the right places is to include them, but you don't necessarily have to. And I'll show you why in a moment. You don't necessarily have to include the j hats and the I hats. But for right now, I'm going to for illustrative purposes. Did anybody get a time? Raise your hand if you got a time. What did you get right up from?
2.0 seconds.
2.0 seconds. Anybody else get 2.0 seconds? Takes 2 seconds. Wonderful. Do we feel all right about that? We feel all right doing horizontal motion. We feel all right doing vertical motion. And the good news is that that's about as hard as two-dimensional motion gets, with the caveat that you have to initially break things into different pieces. Because two-dimensional motion is just a combination of horizontal motion and vertical motion. I'm going to prove it to you guys. I'm going to prove to you that these are the same types of motion. Because if we were to look at some arbitrary velocity vector, we say arbitrary velocity v is equal to vx I hat plus vy j hat, or vx could mean anything, right? It could be positive 2, meaning it's moving 2 meters per second to the right, or it could be negative 3 meters per second, meaning it's moving 3 meters per second to the left. Vx and vy can be anything. We're just using them as standards. Does that seem all right? All right. Well, what this means is that we can have some initial velocity as well, broken up into components the exact same way. I hat plus v I y j hat. So this gives us our velocities. Well, what else do we have? We have accelerations. And we're going to have acceleration being given by some arbitrary horizontal acceleration added to some arbitrary vertical acceleration. And at this point, having those I-hats and those J-hats are incredibly important because it specifies this is the piece that is horizontal. And this is the J-hat is the piece that is vertical. So we have these two pieces. And what do we know? Well, we know for a fact that we can define our velocity such that velocity is equal to initial velocity plus acceleration times time. We know that's how those three quantities are related, and they're all just different forms of the same velocities we've been using. Well, plugging in the pieces that we have, we can write out on the left-hand side Vx I hat plus Vy j hat, that is our left-hand side, is equal to Vix I hat plus Viy j hat. For your V initial term, just taking in the full written out version of these components. Do we see how I put in those two so far? Yes? Seems all right. And then we're going to add to that our acceleration, which is Ax I hat plus Ay j hat multiplied by time. So we get this relationship. And right now that probably looks like a long, complicated mess. But because of how it breaks down, it actually leads us to a really nice and convenient solution. Because when we take all of these pieces and we put them to one side of the equation, so I'm going to take the left-hand side and subtract it over to the right, what we would get is 0 because we subtract the left side to the right, and it leaves us with nothing on the left-hand side. What we'll have is V initial x I hat plus V initial y j hat plus the acceleration ax I hat plus ay j hat multiplied by time. And then you subtract off your final velocity Vx plus Vx I hat plus Vy j hat. There we go. Got a little sloppy there. So just to double check, do you see how we go from point A to point B? Seems all right? You say, well, why did you do that? It seems like you increased the complexity. Well, it's going to start to simplify here. Because at this point, we can combine like terms. We can combine each of the I hat pieces. And what that would tell us is 0 is equal to Vix plus acceleration in the x direction multiplied by time, axt, so we distribute that time term in, and then we subtract off Vx, and those are our three I hat terms. So we combine our like terms, we combine our I hats. We can also combine our j hats. We can say Viy plus acceleration in the y direction times time minus Vy. Those are our j hat terms. All right, well, what good does this do? Well, this tells us from our first principal assumptions of what our velocity and acceleration are related, again, something that we derived earlier in this class, we end up with this relationship. It says, these two things when added together must equal 0. These two things when added together must equal 0. That's a physical must. It cannot be anything other than 0. Without exception, these two things add up to 0. And if that's the case, then we think, well, what can these possibly be? And these two terms, because they have a different I hat and j hat, because they are non-like terms, they can never combine. these two terms can never combine further than this. So the only way for these two terms to add up to 0 is for the two terms to independently be 0. For the two terms to independently equal 0. That means it must be the case 0 is equal to Vix plus AXT minus Vx. And 0 must equal VIY plus acceleration in the y direction times time minus Vy. Those must be true without exception. For any two-dimensional object, so this object is moving in 2 dimensions, for any object that is moving in 2 dimensions, these two relationships must be true. And we rewrite these. We rewrite these because these are in our uncommon form, so we'll rewrite them. That Vx is equal to Vix plus acceleration in the x direction times time. And we have that Vy is equal to Viy plus acceleration in the y direction times time. That's interesting. We went through all of this to arrive at two equations that we've seen over and over and over. So what? What does it tell us? It tells us that these two equations apply regardless of if our object is moving in 1 dimension, which is what we've assumed previously, or if it's moving in 2 dimensions. These equations will always apply. We derive these equations to tell us that these will always apply. And then we say, what's the big deal? Why do we care if these apply? We care because it takes this equation right here, a 2-dimensional equation, a 2-dimensional vector equation, and it takes that 2-dimensional vector equation and essentially breaks it up into 2 1-dimensional problems. 2 1-dimensional problems which are pretty identical to what we've solved earlier. So we think of something like projectile motion tracking an object that is moving through the air. Thinking about any projectile, think that's a complicated movement. Well, it's not actually so complicated because it breaks down into into 2 1-dimensional problems, 2 problems like what we've been seeing so far. So for projectile motion, we are left with the kinematic equations, being the same kinematic equations we've seen before. And this expands out to our displacement equation. The delta x is equal to v initial x plus plus 1/2. Plus 1/2 acceleration in the x direction times time. This applies to even our displacement equations. I could have done the longer derivation to get to there, but I hope that what I've done so far proves to you that you can trust that these equations do apply. So we have our displacement equations, and these tell you about the displacement of any object moving in multiple dimensions. We also have our velocity equations. Vx is equal to v initial x plus acceleration in the x direction times time. Vy is equal to v initial y plus acceleration in the y direction times time. And all of those other kinematic equations still apply as well, yes. Yes, time should be squared on those. Thank you. All right, so this leaves us with just a couple more questions. How do we start to apply these kinematic equations to projectile-type problems? How do we apply these to problems moving in 2 dimensions? For projectile motion in this class, we're going to make a couple of simplifications, just for the sake of making things a little bit easier. What are those simplifications? Well, those simplifications are going to be that we ignore any sort of air resistance and any sort of outside influences aside from gravitation. If we ignore those, then our acceleration becomes 0 I hat plus negative 9.8 meters per second squared j hat. meaning that we do not accelerate horizontally. For this class, we're going to assume that acceleration's horizontal component is 0, and acceleration's vertical component, well, that's going to be negative g. Negative indicating downward acceleration, g, 9.8 meters per second squared, just like it was in free fall. So the earlier question where we had a ball rolling along a tabletop ignoring friction, acceleration was 0. What does that mean? That means the problems are going to be no more difficult in practice than that ball rolling across a table example. Acceleration in the y direction is negative g. Where have we seen that? We've seen that with free fall motion. What does that mean? That part of the problem, the vertical part, is no harder than any other free fall problem. So we take our motion, we break it up into these individual pieces. Do we feel okay so far? We're building up to being able to solve problems, but I just want to double check that we believe these equations apply. If there's any questions, comments, thoughts, or concerns, we make sure to ask them. All right. So then we get to the practical bit. You get to the practical bit. So I give you a scenario. I say a ball is thrown 45 degrees above the horizontal with a speed of 32 meters per second. This 32 meter per second speed with the 35 degree angle, that tells us our object's velocity. We have speed, the magnitude of the velocity, and the direction. So we have a full understanding of its velocity when it is thrown. That means the initial velocity. So we throw an object 35 degrees above the horizontal at 32 meters per second. It's pretty fast, but we give it a nice toss. We set up the scenario, and then from there we ask the question, then we ask the question, how far horizontally does the ball move before it hits the ground? In other words, what is the range of this projectile? So we set up the scenario, throw a ball 35 degrees above the horizontal, 32 meters per second. We ask the question, making a prediction about how far the ball will move when it hits the ground. When we solve these problems, it is always immensely helpful to start by drawing a picture. When you have horizontal motion, we can draw a picture of how our ball will move. So this orange line will represent the ground. Our ball will leave the ground, and when it leaves the ground, it does so initially at a 35 degree angle with an initial speed of 32 meters per second. And then what's it going to do after that? Well, once it leaves the ground, it is going to follow a parabolic path, taking it to the ground level someplace far away. So we draw a picture. Can we see this picture? Does it seem all right? Ball launched 32 meters per second, 35 degree angle. Now we look at this and we say, well, we have a object being launched at an angle. We probably want to break it up into horizontal and vertical components. So we panic because we haven't done this in a little bit. It's been a few weeks. But luckily, you guys have a note card that should be, I believe, pink to represent the vector notation that we will need here. Because at this point, we have a vector at some angle with respect to the horizontal. We want to figure out its x and its y components. So when we take down our knowns, we ask the questions. What are our horizontal components? What are our vertical components? Because we take this two-dimensional problem, we break it up into two pieces. And when we break it up into two pieces, I sometimes like to keep a chart of all the different parts. So we ask the question, what is our v initial in the x direction? Well, it is a 32 meter per second magnitude, 35-degree angle. Look at our note card. We could construct a triangle that would tell us Vix is equal to your initial speed, 32 meters per second, times the cosine, 35 degrees. We all see that on the pink note card, yes? It does use arbitrary AX. But we see that, yes? And we make that connection. VIY, 32 meter per second times the sine of 35 degrees. We've taken our two-dimensional velocity and broke it down into its components, into its pieces, to get its horizontal and its vertical components. Does this seem okay? Are there any questions? Yes?
So we're looking at the cosine one, so AX stands for velocity.
Yeah, when you look at that note card, it uses A to represent some arbitrary vector, right? So A just means vector, right? It could be a velocity vector, an acceleration vector, a position, a displacement vector. It doesn't matter what kind of vector you're looking at. They all follow these same rules. So when we look at that note card that says AX, well, that can represent V initial X, or V initial Y for AY. Or it could represent AX or AY, little a being acceleration. So it can mean anything. So we're taking that abstracted form that's on your note card and making it something specific. So we have enough information to get these values, and you'll do so soon. But that gives you the initial velocities. We know the value. Are there any questions, thoughts, comments? We feel all right about this? We then move on to ask other questions. We say, okay, well, maybe we want to know about the acceleration in the x direction and the y direction. And in this case, in this class, our acceleration in the x direction is what? 0. Absolutely. And the acceleration in the y direction is what? Negative 9.8 meters per second squared. I'm going to write negative g because I'm lazy. So we have our accelerations. That seem okay. We then think about what other quantities might we want to know. Well, you might want to know your, looking at our list of equations here, you might want to know what is your delta x's and your delta y's. You might want to know how far it moved. Delta x, well, delta x is the range, that's what we're actually looking for. That's our horizontal displacement. I'm going to mark that in green because that's what I want. Delta y, well, delta y is something we know from the problem. Delta y, remember, y is your position above the ground, right? Y is how high above the ground are you? When you start, how high above the ground are you? 0. You're on the ground. How high above the ground are you at the end? 0. So we start at 0 height, we end at 0 height. What is our change in height? 0. Now earlier today, we were talking about displacement, and the brave student who spoke out said that displacement was how far you've traveled. That's not exactly true, right? How far you traveled. The ball definitely does travel up and back down. It does travel some distance. But when it comes to displacement, we only care about the difference between your starting and ending position. We only care about where you ended up and where you began. We don't care about everything in between. This is the difference between displacement and distance. All right, so we feel all right about this? We look at this and we ask, well, what other quantities are there? There's some v finals, Vx and Vy. That's the velocity when you hit the ground and the velocity when you hit the ground, horizontal and vertical pieces. We don't know either of these. We don't know what those values are. So I'll put a question mark. And then we have t. T is the time that the ball spent in the air. That is your time of flight. T is the time of flight, how long it was in the air. Now here's the interesting thing about time. When we look at all of these quantities, we have x component, x component, x component, x component. All of these horizontal pieces are strictly in that horizontal realm. All the vertical pieces are strictly in that vertical realm. They don't cross over. The only piece that crosses over is time. Time is the only piece that links together your vertical and your horizontal components. Because it is the time it is in the air, and that is going to be the same for your horizontal and vertical, because it's just how long you've spent in the air. So your time is what links together your horizontal and your vertical pieces. So we list out our components. These are all of our known kinematic components, right? We have our change in positions, we have our velocity and your final velocity or acceleration. These are all of those same motional quantities that we started our class today with, where we were going over what are the quantities. Well, we have displacement, velocity, and acceleration. These are all of the pieces that might be present. So then we ask the question, well, how can we attempt solving this problem? Because we've broken it down now into two one-dimensional problems. And when we look at them, we can solve vertical and we can solve horizontal. I'll use H and V there to represent those are your horizontal and your vertical equations. We can solve these completely separately. So we look and we say, well, vertical. If we look at the vertical pieces, we say Vy is equal to V initial y plus Ayt. We know acceleration in the y direction. We know the initial velocity. We don't know the final velocity. We don't know the time. That's too many unknowns in that equation for us to solve. We cannot use that fourth equation. We say, okay, well, what about the horizontal equation above that? We'll look at this equation that's second from the bottom. Vx we don't know. V initial x we do know. We can calculate it out 35 times or 32 times cosine 35. Plus acceleration in the x direction, well, that's just 0, so it doesn't matter what time is. Also, the second piece tells you is that your horizontal velocity is constant. So we can fill that in if we wanted to. Vx is equal to Vix, but it doesn't really do us any good for our solving of this problem. Coincidentally, that fact will always be true in this class. That fact that your horizontal velocity is constant will always be true, meaning that in this class, this equation will never actually be that useful. So really, when we talk about it solves down to 4 kinematic equations, it's really only 3 because one will never be useful in this class. It just tells you that your final velocity is the same as your initial velocity in the horizontal component. We take a look at the one above that. Delta y. Well, I know what delta y is, right? What is delta y? 0 meters, absolutely. VIY, I know what that is. That's going to be 32 meters per second times the sine of 35. T, I don't know what time is. 1/2 your acceleration in the y direction. Well, acceleration in the y direction is what? Can you remind me? negative 9.8 meters per second squared. Perfect. And then t, again, t is an unknown. But it's the same time that showed up earlier in the equation. This equation, delta y v initial y t plus 1/2 a t squared, that's solvable. That is solvable for time. And then we look at the top equation. Delta x we don't know, t we don't know, so the top equation can't be used yet. However, if we figure out what that time is, then we can use the top equation to find delta x. If we figure out what the time is, we can use this top equation. So how are we going to do that? How we do that is by first solving for time and then plugging it in to the top equation. Seem okay? So, let's go ahead and solve. First, we are going to start off. Delta y is v initial y times time minus 1/2 gt squared. First step is going to be solving that for time, and you look at that and you say, oh my god, that's a quadratic. I don't want to do a quadratic. Well, the good news is that it's not actually a quadratic. Because delta y is equal to 0, what we can do here is divide both sides by t. So we take the right side, divide by t, take the left side, divide by t, and on the left side we have 0 divided by t, and 0 divided by t is going to be what? 0, absolutely. V initial y, that t cancels out, 1/2 gt. We can solve for the time. Now this only works. This only works if your delta y is equal to 0. If your delta y is not equal to 0, then this won't work. If your delta y is not equal to 0, then you do have to solve the quadratic. But it is just a matter of solving that equation for time. Seem all right? We move forward and we say, if that is the case, time, time is equal to what? It's equal to 2v initial y divided by g. Did I get that right? I think I got my algebra right there. And you can figure out how long it's in the air for. Go ahead, solve. Check in with your neighbor. I am going to randomly call on someone to tell me what the time is. I tend to pick on people I see.
this is erasing the
I mean, okay.
Alright, I'm passing around a note card for you to add to your selection. This one, the work got printed pretty small. I wasn't expecting it to be as small as it is. If you have trouble reading it, please let me know and I can print out a few extras, larger prints. Alright, quick show of hands. How many of us need more time to find the time of flight? Alright, well it looks like majority rules. We will move forward. Alright, so what is the time of flight? 3.7 seconds. How many of us got 3.7 seconds? Wonderful. So we have 3.7 seconds. What does that mean? That means that it's in the air for 3.17 seconds before it hits the ground. Now, like I said earlier, yes?
Could you remind me why gravity is not negative?
It is negative, right? Negative 9.8 meters per second squared.
I think you were looking at the T equation.
Over here?
Yeah.
So when we go from here, right, we take our negative 1/2 gt squared. I will do the algebra real quick. And what we're going to do to solve this equation is add 1/2 gt to both sides. Because that will take what's on the right-hand side over. It is negative g. The negative is outside of that 9.8. What we end up with is 1/2 gt is equal to v initial y. And then from there, you just multiply the two, divide by g over t. T is equal to 2 v initial y over g. Now, it needs to end up being a positive value. Your times should always end up being a positive value because it hits it 3.2 seconds into the future. What was it? 3.7 seconds into the future. Yes?
Just 3.8 seconds also acceptable.
Yeah, that's probably just a difference in rounding. 3.7, 3.8. Double check when you do these. You are in degree mode. You'd be off by a lot more if you use 37 in radian mode. But just always double check that you're in degree mode when you're using degrees inside the sine and cosine function. 3.8 it sounds like rounding error to me. All right, so we found 3.7 seconds using our vertical components. Now again, that time is special. Why? Because that time is what bridges the gap between your vertical and your horizontal motion. That means your vertical time is your horizontal time is 3.7 seconds as well. And suddenly, we have enough to solve for this top equation. Why? Because v initial x, we know, is 32 times cosine 35. T is 3.7 seconds, and then this other term ends up being 0 anyway. So we can now find our horizontal range, delta x. So let's go ahead and solve for that. So I will put it right here in this bottom corner. So we find our time, and once we have our time, we'll say delta x is equal to v initial x times time, which is going to be 32 meters per second times the cosine, 37 degrees, multiplied by the time, which we just found, 3.7 seconds. Let me figure out how far the ball travels. Yes?
You put cosine 37, is it 35?
It is 35. Sorry, I'm seeing 3.7, 32, 35. Mixing some stuff up, I apologize. But it is cosine 35, thank you for the correction. We figure out how far it goes. How far does our ball land? Was it? 97 meters. Raise your hand if you get 97 meters. That sounds perfect to me. Travels about 97 meters before hitting the ground. You set up a scenario. I'm going to throw the ball at this angle at this speed. You ask the question, how far does it go? You make the prediction with these mathematical models. Now, do the questions get harder? Yes. And the one place these questions will get harder is that this delta y might not equal 0. If delta y does not equal 0, the only thing that changes is you have to apply the quadratic equation. So I'm going to ask you guys to make sure that when you go home that you brush up on that quadratic equation, because it might be relevant in these projectile motion problems. So are there any questions, any thoughts, any comments? A little bit of time, so after my recap I might give you a quadratic equation to solve. Yes?
How did you get the simplified delta x equation where it's just v initial x?
So what this equation comes from is that your final position is your initial position plus v initial t plus half a t squared. Right, this is what's on your equation sheet. What I did here is I subtracted over x initial and displacement is the quantity that tells you about your change in position. What do you know? You have final minus initial position. That's your change in position. That is your delta x. So it's just taking that equation, taking x initial to the other side by subtraction, and then x final minus x initial is your delta x.
I'm just confused how you got from that to it just being v initial x times t. Like,
Okay, so we have plus 1/2 acceleration in the x direction time squared, yes? What is the acceleration in the x direction? 0, and then 1/2 0 times time squared is going to be 0. So just like that horizontal problem with the ball rolling across the table when we first got here, same process. Same process that tells you acceleration is equal to 0 leads you to this behavior. So same exact reasons of why the ball rolling across the table gave us that same equation. All right, any other questions, thoughts, comments? Yes?
So the projectile motion equations, can they be at all to any rotational motion problems?
It can, but the problems become a little bit more complicated to do. These equations, right here and here, those are always true, not just with projectile motion, but with all motion. Provided your acceleration is constant, that is always true. Now with rotational motion, the best way to define your accelerations is in a spherical coordinate system like what we did. When you start to define things in a different coordinate system, then your acceleration is probably changing direction always, which means that these equations don't necessarily apply. Unless you're really clever about how you apply them. So when you're dealing with rotational coordinates, it's almost always best, rotational motion, it's always best to do it in those rotational coordinate systems, theta, omega, and alpha. But technically could. Any other questions? All right, so just to kind of recap with us. just to recap, when we deal with motion, we're talking about velocities, acceleration, displacement, and these are all vector quantities that can exist in multiple dimensions. And while these can exist in 2 or 3 dimensions, those 2 or 3 dimensional motion problems can always be broken up into their what we call orthogonal coordinates, meaning your horizontal and your vertical. Those are orthogonal. And your z direction also orthogonal. So you can always break them down into their component directions. When you do this, those same kinematic equations that we've seen previously will show up again. Same kinematic equations we've applied show up again. But when we have this motion that's 2-dimensional, it's essentially 2 one-dimensional problems linked together. How are they linked together? They're usually linked together with time. So when you're solving these problems, any sort of a 2-dimensional problem, when you're solving them, you can treat your horizontal and your vertical components separate but linked with a time. Once you do that, you can treat it as though we're a free fall problem, like what we saw at the beginning of the lecture, in addition to a horizontal problem, like what we saw with the ball rolling across the tape. So we take this 2-dimensional problem and we break it up into 2 simpler 1-dimensional problems. If we had a 3rd dimension, it would just break into a z component as well. But we're not going to do too much of that. Feel okay about this? Any thoughts, any comments? If we have enough time, I'm going to change this problem up on you. How am I going to change the problem? I am going to say we launch a ball off a cliff. We launch a ball off a cliff. This cliff is going to be 20 meters high. The ball launches off of the cliff. It's going to follow a projectile path and land somewhere in the bottom region of the cliff. This is the case of motion, which has a different starting height than an ending height. But we can still ask the question, what is its range, what is its horizontal displacement, delta x? We can still ask that question. When we do this, we set up the problem, and this problem sets up much the same way. We still have the same initial velocities, because we didn't change the speed, we didn't change the angle. We look at this and we still have the same accelerations. It's still projectile, still moving with those same accelerations. The difference now is that you have some delta y. In this case, you start 20 meters above the ground, you end at the ground level, you've moved 20 meters downwards. That means that your delta y is negative 20 meters. And the negative is important. It tells you that you're traveling downwards. What does this do? Well, this is going to change your time. It's going to be in the air for longer than 3.7 seconds. How long? Well, you would determine that by going back to this free fall equation, where now we say delta y, negative 20 meters, is equal to v initial y, which is going to be that 32 meters per second times sine of 35, whatever that value comes out to, minus 1/2 gt. I'm going to put in the 9.8 here. I just didn't put in the v initial y because it's going to be a little bit longer of a input, and I don't want to squeeze it in too much, but that is just a number. What is this? This is a quadratic. This is a quadratic equation. What I want you to do in these last 5-ish minutes, solve this quadratic equation for time. Remember, was it x equals negative b plus or minus b squared minus, x equals, oh my god, I can't remember the quadratic equation. Hold on, I know this. my god, I am blanking. What's the quadratic equation? B squared minus 4ac. Thank you. All over 2a is equals negative b plus or minus square root. All right. Something like that is your quadratic equation. And an example of a quadratic, negative 20 meters, the initial yt, 1/2, 9.8t squared. Go ahead, solve this for the time. You'll get two roots. You'll get a negative root and a positive root. The time is the positive. You cannot have negative times. Solve this for the quadratic. Once you're done, you are free to go. I'll tell you what the answer to this quadratic is momentarily. Before you leave, a couple of notes. I have homework to return as well as homework to collect. Homework to collect will be over here on this right-hand side table. Make sure to drop your homework off. Homework to return will be on these tables over here. I've separated them by last name. Last name A through D will be far right side of the table. Last names E through L will be in the middle of these two tables. And then last names M through end of alphabet will be on the far right-hand side table. I'm trying to spread it out a little so that we don't congregate too much. Make sure to grab your homework, your previous homework, before you head out. All right, it's all for time. I'll give you guys a few minutes to do so. Once you do, collect your homework and you're free to go.